me to give this sort of overview on what's going on in this program. And so I thought I'd give you essentially a description of why the CGM is an interesting thing to study, the CGM being the circumgalactic medium, okay, which, as the word might suggest, is the stuff around, but not too far away from galaxies. This presentation is, I'm going to, in true Blackboard fashion, I'm going to use my teaching mode where I just set up a whiteboard and I'm going to just talk on the whiteboard. All right, so there's no visual aids here. Okay, we're going to sketch and we're going to have fun with this. And this is intended to be very interactive. I'm going to try to pitch it at a level of, you know, a general physics audience, not specialist. But please do interrupt, ask questions, use the raise hand feature, or just pipe up if there's some interesting thing you'd like to know. And this can be pretty free form. I don't think I really have 45 minutes worth of stuff, you know, prepared to say in advance. We're just gonna kind of see where this goes. Hey, Lars?
Yeah, that's great.
Sorry.
That's great, Romeel. Yeah, I will. I would just encourage people to break in so that you don't have to worry about watching for hands.
Yeah, please do. Please do. Okay, great. All right. Well, let's get going. All right. So, let me set up here. What's going on in the CGM, Circumgalactic Medium? All right. So, this conference, Halo 21, is basically about understanding gas that's in the circumgalactic medium. This is otherwise known as halo gas, hence the name Halo 21. And I think I'd like to basically hope that you come away with from this presentation, understanding why the CGM is really one of the frontier areas of understanding how galaxies form in our universe. Galaxies, as you probably know, are kind of the way we mark out the universe. They're the brightest things we see in large numbers. The way we sort of understand the evolution of the universe. The way we try to constrain cosmological parameters, like maybe you've heard of dark energy, dark matter. So all of these things it's sort of crucial to understand how galaxies form and evolve. And I think there's come to be a growing realization that the circumgalactic medium turns out to be the real uncertain part of what we don't currently understand about how galaxies form. So let's see how we've gotten to this situation. So when we talk about galaxies and sort of, you know, overall the universe in general, the first thing we have to start with is a little bit about cosmology. So cosmology, of course, is an area that has grown tremendously in the last 20 years or so. And the thing I won't go too much into detail on cosmology, but the point I want to make is that we now understand the constituents of our universe fairly well. So our universe is made up of, I'm going to start with about 5% what we'll call baryonic matter. Okay, this is, again, an astronomer term, which is not exactly equal to the proper physicist term. Okay, baryonic matter to an astronomer is anything that interacts electromagnetically via ENF, right? So it interacts with photons, okay? And that only makes up about 5% of the total mass energy content of our universe. About 25% is dark matter. And this is this as yet unknown subatomic particle that, as far as we can tell, does not interact with photons. Okay? Then, of course, there's 70%. The remainder is this stuff, dark energy. I won't worry too much about this today. It is, of course, important for how galaxies grow and the overall structure of the universe, but it's not going to be so crucial today. And essentially, our best models of this remain to, you know, unfortunately, in some sense, Einstein's old cosmological constant, which can be thought of as a vacuum pressure. Okay. Now, the number I want you to really remember from this, right, is the ratio, and we astronomers often denote these by omegas, okay, so omega baryon for omega B, omega dark for dark matter, and lambda is typically the symbol used for dark energy. Now, these two are matter components, right, which means that they have mass. Okay, so if you want to think of it in terms of an equation of state, they behave with an equation of state corresponding to matter, to mass. Okay, well, it's different than dark energy. So the thing about matter is, of course, that it responds to gravity and it clusters in a way that that gives rise to things like galaxies and so on and so forth. Now, the thing to keep in mind is that the ratio of omega B to omega matter, where omega matter is going to be the sum of omega B plus omega dark, so it's about 30% total, okay, is now known to very great precision. And this number is about, I won't say the exact number, it's known to much better precision than that, but for our purposes, say it's about 1 to 6, okay, which means that, obviously dark matter comprises most of the mass in the universe, and the baryons only comprise about 1/6 of the total mass. Okay, so this is the setup that we have, right? In cosmology, we have these constituents. We have perturbations that are set at the very early epochs. We see these fluctuations in sort of, if you know about the cosmic microwave background, we can see the fluctuations in the matter at a very early time. Those fluctuations then grow to form galaxies. So this is the setup. I want you to remember that 1/6 number. So now let's talk a little bit about galaxy formation. So how do galaxies form? Again, this is all just sort of setting up the problem here, okay? Okay, so how do galaxies form? Well, you start off with some kind of slightly overdense region, let's say. So this is a representation of density versus some coordinate, let's say, just some spatial coordinate, right? You start off with some slightly overdense region. Well, what happens in that overdense region? Well, the thing it's going to do is that overdense region has a little more gravity than the surrounding region, so it's going to pull matter in. As it pulls matter in, what happens to that region? It becomes more overdense, okay? Rich get richer, and you get more and more overdense, all right? So this is known as gravitational instability, and it stops when you get a sufficiently dense region that the gravitational infall drives the mass that's falling in to a velocity dispersion that is able to balance the gravitational potential, okay? So essentially what happens is that as this material falls in, once it becomes sufficiently dense, it achieves such a high velocity that the velocity dispersion that results within this little region up at the top here is sufficient to no longer allow it to collapse. And we call these virialized regions, and we call the term that astronomers use for this is halo. Okay, so a halo is a region of space in which all the matter essentially obeys the virial equation, and therefore is sort of static there. Okay, so let's take a look at one of these halos. I'm going to sort of draw a boundary. It's a terrible circle here. So let's draw that again. So here's a halo. Here's my halo, okay? And stuff is falling into this halo as it grows. And what can we learn about this halo? Well, one of the things we can learn about this halo is that it's going to have, because the surrounding matter is made up of the gravitational parts of it are the dark matter and the gas. So the gas and the dark matter are all going to fall in, right? And so this halo is going to have roughly made up of, in principle, about 1/6 baryons and 5/6 dark matter, right? So again, right, all it's just so far the only story is gravity, right? So there's no reason that the baryon should do anything different than the dark matter because it's all just responding to gravity at this point. However, once it gets inside the halo, several things can happen. Now, the dark matter ends up with some velocity dispersion. So it ends up with some velocity dispersion sigma. So the dark matter has sigma dark matter, and the gas then, of course, is being accelerated, but the gas, of course, smashes into each other. It shock heats, right? And so this shock heating leads to a virial temperature for the gas. So the gas has a T virial temperature, which is roughly such that KT is up the order of, sigma squared. Okay, so KT, and so this is basically just equipartition between the thermal energy and the velocity dispersion. So, and the random motions. So the gas has some virial temperature, and again, just to give you some idea of what the numbers are, for something like the Milky Way, the virial temperature is around 10 to the 6 Kelvin. Okay, so 1,000,000 degrees Kelvin. For a big galaxy group, it's about 10 to the 7 Kelvin. For a dwarf galaxy, maybe it's about 10 to the 5 Kelvin, so on and so forth. And then maybe for a big cluster, it's something like 10 to the 8 Kelvin. So that just gives you a range, an idea of some of the range of the temperatures, and we'll come back to why that turns out to be important. So inside this halo now, you have dark matter, you have gas at this virial temperature, and the halo now sets itself up in some sort of a hydrostatic equilibrium. So if we draw a density profile in this, it turns out, the density profile is going to look something like this. Okay, so you're going to have some sort of a core that's isothermal, and then you're going to have some sort of a drop off in the outskirts. Now, if you think about it, right now we're going to have the baryons do something different than the dark matter. Right, this is where the property of the baryons being electromagnetically interactive comes in. So how does that come in? Well, that means that if you get to sufficiently high densities, this baryons, right, can undergo collisional processes and start cooling, right? Start radiatively cooling. So there's some radius within which the baryons can cool quickly, relatively quickly, compared to, let's say, the dynamical time of the halo, right? So within this region, the baryons within this region, what do I mean by cooling? I mean, you have a collision, you excite an electron, the electron drops to a lower level, emits a photon, right? And as that photon goes out into space, it carries energy with it, and therefore the baryon loses pressure support, right? So it falls down towards the middle. As it falls towards the middle, right, it conserves angular momentum, and so it's sort of it's like the skater pulling in their arms, and you end up with something that looks like a disk galaxy in the middle. So you have this cooling radius out here, and within that cooling radius, you end up forming into some sort of a disk galaxy. Okay, so this is the picture of galaxy formation that was developed in the 1970s. And it does pretty well, right? You can see what the origin of things like spiral galaxies are, like our own Milky Way. The numbers of the sort of galaxies that come around, the relative numbers of different sizes of galaxies, kind of work out reasonably well. The sizes and the spin rates of the disk work out really well. So everybody was pretty happy until, okay. So now it all sort of goes wrong. Okay, so where does this scenario go wrong? So let's think about.
Romeel, I'm going to interrupt for a minute and just see if there's any questions. This is maybe a good point.
Yeah, this is a good point, actually. Is everybody with me so far? Okay, so far what we've got again is a halo. It's filled with hot gas, except in the middle region, where you can cool and form into this disk galaxy. Okay, and in this simple model, the halo is made of 1/6 baryon and 5/6 dark matter.
And Romeel, real quick on that, since you can go back, which is like magic relative to a Blackboard, can you remind everybody of the scale of the galaxies? I know it's for the
yes, right. Sorry,
it's a great scale, so it might have no meaning, but it doesn't hurt to say.
Yeah. So well, I'll do it in light years, so that, since parsecs is maybe. Yeah, typical galaxy scale, like the Milky Way, we sit at the sun sits about 25,000 light years away from the center of the Milky Way. So that gives you an idea, and we're sort of not in the total outskirts, but we're sort of, in the suburbs, basically, of our own galaxy. So that gives you an idea of the scale of the galaxy. There's something like 25,000. The scale of the halo is more like 200,000. Okay, so sorry, no, for in light years is more like 600,000-700,000. Okay, so the halo is much larger than the galaxy. I've not quite drawn this to scale, but it's pretty close. Okay, so is that what you were asking, Lars?
Yeah, that's great. I think just to give people
a sense of the scale. Okay, so now people started to go, okay, great. So if we have all these baryons in the halo, well, can we go find them, right? Baryons are things we can see. They're things that are in the periodic table. In point of fact, in the universe, it's about 75% by mass hydrogen and 25% by mass helium. Helium's kind of hard to detect, but the hydrogen's pretty easy. And then there's about, within halos, maybe 1 or 2%, maybe even less, that astronomers called metals. So yet another astro misnomer. So metals is basically any element heavier than helium, according to an astronomer. So basically, we can go and try to find all the hydrogen, and assume that there's comparable amount of helium or whatever proportional amount of helium, and go try to look for the stuff. So what are the different forms that baryons can take? Well, the most obvious form that you can have for the baryons is the stars, right? So you can have stars, but that's not all. Of course, the baryons could still be in. I'm going to separate this out into sort of cool gas, and I guess yellow is not going to show up very well, so let me use green for hot gas or warm gas. And then there's other components like black holes and dust. Dust is again another astro misnomer about anything that's a molecule that astronomers basically call dust. So we can go and try to add up these fractions. And so inside of halos, so we go to halos of different masses. So again, by convention, everything is always logarithms because otherwise, and this is the logarithm of the fraction of mass contained in these various components. And what I'm going to do is I'm going to mark this point here as the 1/6 value, right? So this is I'm going to multiply all these things by this constant baryon fraction. So basically, if I add up all the different types of baryons in a halo, and they really do add up to 1/6 of the mass, as one would expect, everything would lie along this line. Okay? Here's what the data actually say. So we first we start by looking at the stars, and it looks like something like this. Oh, sorry. All right. There's a peak right around here. This happens to be about 10 to the 12 solar masses in halo mass. So this goes down to maybe 10 to the 10, and this is up to 10 to the 14 up here. So 10 to the 12 is actually right around a Milky Way, as it so happens. Okay, and this is a big cluster of galaxies, and this is a real small dwarf galaxy halo. So the maximum that the stars ever reach is maybe around 25% of this cosmic baryon fraction, right? Oh, well, okay. Well, if it's not in stars, maybe it's in something else. Well, you can go add the cool gas in. This is what the cool gas looks like. Essentially, there's a little bit of cool gas in small galaxies. It increases a bit as you go to lower masses, but it's not much, okay? The hot gas is a little bit harder to calculate. It certainly goes up here in the large halos, okay? Hot gas you usually see via X-rays. And so you see hot gas in the X-rays, but you definitely see that even the hot gas doesn't really add up to the total baryon fraction, even when you get down below about 10 to the 14 in halo mass, right? So look at this huge gap. This is like 75% of the baryons are not in the things that we see inside of galaxies. So all these are like galactic baryons, right? These are galactic components. Okay, so there's two options here, right? Option one is they are the baryons. So the question then is, where are the baryons, right? Where are they? If the halos are supposed to have all these baryons, they are maybe in a form that's difficult to detect in the CGM. So this is all the CGM. This might be the CGM gas, right? Or two, they're gone. They're out of here. They've been ejected out of the halo. Now, wait a minute. Okay. Now, already these numbers are very surprising. Why is these numbers very surprising? Well, first of all, you can think about the number for stars or cool gas, or the amount in the galaxies altogether. It turns out that the dynamical time, the infall time from a halo's virial radius down to a galaxy, right? The dynamical time is roughly something like 1/5 of a Hubble time. The Hubble time being the age of the universe at any given time. That means that you would expect about 20% of the mass of the baryons in the halo to be in transit towards the center, and about 80% should already be in the middle in galaxies. So a naive model, and in fact this works out from simulations and stuff like that, if you don't do anything else and you simply let the baryons fall into a halo, cool at the middle, this number shouldn't be 25%, it should be more like 80%. Okay? So Jess asks, could they never have fallen in the first place? Yeah, sure. So they're gone, meaning that they were either ejected out or, so there's two options here: ejected or never fell in, right? So already the amount just in the galaxies is very surprising. And this has basically spawned what to this day is essentially the key question in galaxy formation. Why is galaxy formation so inefficient? Why is the amount of baryons in the galaxies that we can really see? We can see galaxies pretty well, and we can count baryons in them quite efficiently. Why is it not around 70 or 80%? Why is it at most like 25%? Maybe if you push things 30%. And so the way that this is basically thought about, right, is the idea that galaxies are self-regulating systems. So maybe I should actually, this is another good point to sort of stop and make sure that everybody's kind of on with me here. So is everybody sort of clear on what the main problem is here? Any other questions or thoughts about this?
Yeah, this is great, Romeel, but let's pause. Indeed, it's good time to pause. All right, your stunning clarity.
Perfect. All right. I wish my students were so attentive and so what is going on here? Well, clearly, if stuff isn't falling in when it's supposed to be, there has to be something that is preventing it. Either there has to be something that's preventing it from falling in, or there's something that has to, once it falls in, has to kick it back out. Both of these things require energetic input from something, right? You need energy to counteract gravity, because gravity always works. And if you just let things go, gravity will just keep pulling things in. If you're not going to, let that happen for some reason, you had to have injected some kind of energy. So let's think about what are some of the sources of energy that you can get that become comparable to the kind of energy that you need in order to actually, affect the amount of baryons, like 50% of the baryons in the halo. I mean, you're really affecting a lot of mass here, right? Either in the preventive form or ejective form, something. Either they, and so it's really quite a stunning energy budget that you need. So what are some of the key things that you can do? Well, one thing that we know releases a lot of energy is stellar death. And stellar death causes, well, if it's a sufficiently massive star, these stars go supernova. And when they go supernova, the energy they release is about 10 to the 51 ergs. Okay, so that's a big number. Okay, and you can show, and this is some work that was done in the 1980s, that that for small galaxies where the potential wells are small, and by small galaxies I typically mean around M halo less than about 10 to the 11 solar masses, so not quite Milky Way size, but smaller than that. You can basically calculate that the binding energy of the gas in the halo is less than or equal to the energy that you got out of having all those stars form and go supernova that you see in the galaxies. And this is basically because the smaller halo you have, the lower your potential well. And so if you're sort of putting in a fixed amount of energy per unit mass of stars that you form through the supernovae, you're basically going to be able to unbind the gas at sort of low for low potential wells, small potential wells. So that's pretty good. But again, if we go back here, right, we're talking about stuff down in here, right, 10 to the 11 and below. So still doesn't really explain this 25%. Well, what other energy sources can we envision, right? The second is black holes. Okay, so we haven't talked much about black holes yet, but probably most of you know that every galaxy of any sizable mass has a big supermassive central black hole in the middle, and that when that black hole accretes, the accretion onto that black hole releases energy from the accretion disk in a variety of forms. And I'm going to use the term AGN, so I'll introduce another buzzword here, which is active galactic nuclei. That means that when the black hole is accreting, you see that the nucleus of the galaxy, the very central region where the black hole lives, is active. It's emitting a lot of energy, and that energy might be something that is able to help with this problem, right? So again, the amount of energy in the black holes that you can potentially release out of the black holes is enormous. I mean, it's E equals mc squared, right? So this is in principle, you have incredible amount of energy. Actually getting it out of the black hole, that's a little bit trickier, okay? But the point is that essentially, if you get sufficiently massive black holes, if you get your mass of your black hole greater than about maybe, I would say conservatively 10 to the 8th, but maybe more like, few times 10 to the 8th. Let's just call it few times 10 to the 8th, right? Once you get this massive a black hole, then the accretion energy, again, becomes, comparable to the binding energy of the gas, right? So, 4 typical types of, black hole accretion, right? So the problem with this, right, is that those massive black holes really only occur in galaxies sort of in this region over here. So for instance, the Milky Way's black hole is only about 4 million solar masses, right? So that's way below a few times 10 to the 8th. The Andromeda galaxy, which is our nearest big neighbor and, a somewhat bigger galaxy, that has a black hole that's maybe a couple times 10 to the 8th. Okay, so it's starting to get in that range. But again, this really doesn't explain this whole intermediate region. You can do it in dwarfs. You can sort of do it up here in the massive systems, but trying to fit this all together in sort of one seamless puzzle is really hard, right? And models have been struggling with this, basically for the last 20 years. So basically, we have these two forms of energetic input, but there's got to be something else, right? And what is that, right? You can think of other things like stellar winds. You can think of cosmic rays. You can think of, a number of other different possibilities. But, they're really, well, not much is known about those things, or at least less is known on sort of large scales about the impact of those types of things. And it doesn't seem that, at least if you were put in simple numbers, it doesn't seem that promising that you can get this all to work out. So again, this is sort of the basic problem that we have, right? And the hope is the CGM the clue to solve this, right? Because if we can actually observe this gas, this missing 50%, and we can say that it's there, but it was just hidden from us somehow, or we can say that it's conclusively not there. That would also be interesting, because that would tell us more about what kind of energetics we need, right? So, we have these sort of questions of, where, well, as we've said, where are the baryons, right? And we also can like think about using other tracers for how these baryons are actually how the energetics have worked. So for instance, one of the things about Superdome that's kind of fun, right, is, you probably heard the Carl Sagan quote, we're all made of star stuff. What does that mean? That means that our heavy elements were all generated, our metals were all generated in supernova. Well, that means that if supernovae energy is the thing that's driving the CGM gas, or driving out the gas from the galaxies into the CGM or beyond, or at least providing the energy, then that should be accompanied by a whole bunch of metals. So we can try to look for the metals, right? The heavier elements, which we know had to be produced in the supernova. So they can act like a calorimeter, effectively, almost, for how many supernovae have gone off, right? And maybe that can tell us, constrain the energy budgets of these things, right? So, and then, things get much more complicated when you start to look in 3 dimensions, unfortunately, as often happens. So, this one-dimensional spherical cow picture was pretty nice for the 1970s, but as soon as people started doing, full numerical simulations of these things in the 90s and the 2000s, they realized that the CGM actually looks a heck of a lot more complicated. So if you have your halo and your galaxy down here, we might have inflow flowing in along sort of large filamentary structures. So we sort of have these sort of inflow patterns that are coming in along these large filamentary structures. And these filamentary structures are sort of a natural outcome of this gravitational instability process that I talked about, that's not, if it's not completely spherically symmetric. So you can have these stuff coming in, but then if you have material coming out, right, the material is probably going to come out sort of along the path of least resistance, if you want to think about it, right? So if you sort of try to blow material out, it's not going to try to blow directly against these filaments. It's probably going to try to blow in between these filaments, right? So these are galactic outflows, right? And so these are galactic inflows, right? And so the idea is to then be able to map out, ideally, right? We'd be able to map out the stuff with inflows and the stuff that's going out. We'll be able to take a census of it. We'd be able to get how much mass is going in, how much mass is coming out, where the mass ended up. Maybe we can look beyond the halo and say, did the mass end up farther away? You might be able to do this with things like weak lensing, so on and so forth. So in the last sort of few minutes, I just wanted to outline some of the ways that people try to observe all this stuff going on, right? So again, let me go back to black here. So observing the CGM, right? So again, ideally, ideally we like to either model it or, in some robust way, but there appear to be too many uncertainties here, and at least the simple models don't seem to work all that well. So let's try to go and observe. Let's try to actually empirically calibrate what's in the CGM and what it's doing, right? So what are some of the ways to do it? Well, the ideal thing would be to see this stuff in emission, right? You'd be able to say, oh, this stuff is just, going out. And, here's the big outflow chimney or something like that. This is very hard. Why? The gas is too diffuse for the most part, right? And typically emission measures, which are again just a product of radiative cooling, these are goes as density squared, right? So it's proportional to density squared. So the more common way these days is to use absorption. Now, what does that mean? So that means that imagine you had a halo of gas here, and imagine the universe was so convenient as to put a very bright object behind it compared to you standing over here with your eyeballs and hopefully a telescope. And this line of sight then comes right through the CGM to you. Now, this quasar, typically you use a quasar because these are the brightest things. It doesn't really matter what the flashlight is. But if there are elements in here like hydrogen, we know there's probably hydrogen here, right? So the hydrogen, the hydrogen, the helium, there aren't too many lines. It's, it's a noble gas. It's kind of annoying to try to detect it. But you can look for some of the metals. Particularly oxygen is the most common metal. Carbon is another common one, silicon, so on and so forth. So what you're looking for then is you take your quasar spectrum, which maybe looks something that looks like that, let's say, and it has a peak at the Lyman alpha emission of the quasar itself. And what you're looking for is at the redshift of the galaxy. So this is where the galaxy is in wavelength. So this is wavelength versus intensity of the quasar. So it's a spectrum, right? What you'll see is absorption. You'll see a bite taken out by the gas, by the hydrogen and metals that are in the CGM along the line of sight. So this is the most common way to do it, okay? But it's really hard, right? You have to get exactly the right lineup. You have to get the quasar going through the CGM of a galaxy, and the fact is the covering fraction of galaxy CGMs is not actually that large on the sky. Most of the sky is just black and empty. So it's actually hard to get these coincidences. Then you have to go and be able to get a high resolution spectrum. And here's another thing where nature has been super annoying to us. Most of the strong transitions of these lines, which can give you very nice absorption, are in the ultraviolet. So for those atmospheric scientists, the ultraviolet is unfortunately does not penetrate the Earth's atmosphere, right? Which is a good thing for humans, but not so good if you're trying to study CGM, right? So there's two options. One is you can throw a telescope into space, like Hubble Space Telescope. So the Hubble Space Telescope has been huge for this types of studies. The other is you go to higher redshift. If you go to higher redshift, then for instance, like the hydrogen line at 1216 angstroms, right? If you go to redshift 2, this goes to, 1 plus z times 1216, so about 3600 angstroms, right? And that 3600 now puts you just into the visible outside the opaque atmosphere, right? So you can either do this with big telescopes on the ground at high redshift, which is a bit annoying because everything is faint far away at high redshift, or you can do it locally, but then you have to go to space, right? So this is what makes it particularly complicated. So that's how that's why it's sort of complicated to try to detect it. The other big effort, of course, comes in try to model the CGM, right? and try to understand exactly how all these inflows and outflows and all things work together. So you have to, of course, use hydrodynamics. And we have to do it usually in 3D, okay? So you can see this is already going to be difficult, but we have to include all kinds of processes we don't understand. So we have to include star formation, have those stars go supernova. We have to put in black holes. And then we have to, model all these things with these fast moving inflows and outflows and all the surface instabilities that occur. We have to worry perhaps about, I hate to say it, but magnetic fields, right? All of these things could potentially be important, right? So it's a very complicated and difficult problem. So ultimately, this is basically what this Halo 21 conference is about, right? It's about trying to understand what is the latest in trying to observe the CGM, trying to do things like we had a whole day led by one of the UCSB faculty, Crystal Martin, that was talking a lot about orientation, right? So orientation such that, well, we expect inflows to occur along the plane of the disk and outflows to occur perpendicular to the plane of the disk. So maybe the angle between the absorption line and the disk can tell us whether something is an inflow or an outflow, right? So these are the kinds of things where we're trying to take the very limited data we have, put it into very complicated models, and the other big thing is that in order to model individual absorption lines, something like if you want to model, O6 happens to be a very strong line. O6 is 5 times ionized oxygen. Well, you have to model ionization, right? So this can come from photoionization, collisional ionization, all kinds of things. So this is why the problem is interesting from a physics point of view. It's extremely complicated. The observations are there, but they're not like super constraining yet. And it's absolutely a critical problem for understanding this very fundamental question about galaxies, which is why is galaxy formation so inefficient? So yeah, I think I'm sort of out of time and I'm kind of out of things to talk about, actually. So I think that's a good place to end.
That's great, Romeel. Thank you so much. Great talk. Great talk. Great story of challenges being faced in your program. So let's get a question from somebody not in the program. Pat.
Yeah, thank you for the great talk. My question is, you mentioned magnetic fields with the tone that it's a bit of an afterthought, but where there's supernovas, there's probably cosmic rays.
Yes.
And that must be a substantial player in this, both in energetics. And then there's the cosmic rays will interact very strongly with the magnetic fields. And now it's notoriously difficult to trace the origin of cosmic rays precisely because of what I just said. But the question would be, in a sense, what's the story there in this in terms of the effect of cosmic rays and how they're exploited?
Super good question. And in fact, this is one of the hottest topics, I think, in the current modeling of the CGM is understanding the role. So first of all, including magnetic fields in these cosmological scale models is basically something that's only become possible in the last, few years. Like by few, I mean like 3 or 4, something like this. And then, of course, we have to have some model for generating the cosmic rays when you want to put it into these models, which is, as you say, fairly uncertain. The biggest uncertainty right now is in how the cosmic rays couple to the gas. So it's clear energetically the cosmic rays could be potentially very important, just like black holes could be very important. So, it's almost like we have too many things here. But the real uncertainty right now is this coupling constant effectively between how the cosmic rays are going to be able to drive the bulk of the gas. We need it to couple to the hydrogen, right? We need to couple it to the hydrogen. In order to do that, it has to couple probably, to ionized gas, and so on and so forth, right? So it's absolutely a really interesting problem. I would say that the preliminary results are actually kind of encouraging. And one of the cool things about cosmic rays is they have a long mean-free path.
Indeed.
So, sorry?
No, indeed, yes.
Yes. And that's really helpful because if you think about it, one of the big problems with, imagine you're inside a galaxy here. Okay, I'm just going to draw, you're inside a thin disk of the galaxy. And you set off a big supernova right in the middle of that thin disk, right? Now, the problem is that if you dump all this thermal energy right here, you're going to, first of all, be dumping it into really dense gas where it's going to radiatively cool and lose all your power right away. If you have to manage to get some kinetic push and a breakout, even then, what happens is that, you don't actually, you don't actually carry a lot of the mass out with you, right? These supernovae explosions tend to blow channels instead of really, carrying a bulk of a mass out of a galaxy. But cosmic rays might behave quite differently. Cosmic rays can sort of, because they have a long mean-free path, they can provide a more spherical push outwards that could, drive things on much larger scales. And potentially you can get coupling out to, the initial model suggests maybe, 30, 50, 1,000, maybe 100,000 light years. So well into the halo now. And so I think it's a very promising area that's really just starting to be explored. But I think the real uncertainty right now is understanding how the cosmic rays couple to the gas and having that actually drive a bulk outflow.
Mm-hmm. All right.
David, you have a question? David Hughes.
Yes, thank you. That was very interesting. I wonder if I could just ask you a bit about your model. I mean, you've got this model here, which has got everything in it. I mean, as you say, it's got supernovae and black holes. So, there are people that, as you know better than me, the people that study just supernovae, and they do huge numerical simulations of one supernova. But presumably a supernova in your grand scheme here is a very tiny thing.
That's right.
So how do you parameterize all these things into your model?
Very crudely is the bottom line answer. So you're absolutely right, and so I think that we're trying to. I like to think of it as sort of building a layer, stacking a house, right? You start with the bottom where you have the very high resolution simulations of things like people who study supernovae or people who study black hole accretion. And then you try to develop, what you try to do is develop what amounts to an effective theory, right? To say that, okay, under these conditions, the supernovae will dump this much energy on larger scales. Even though we may not get all the details of how the supernova propagates and do all that, but if we get the sort of the bulk energetics of it right and the directionality maybe of the energetics, then we can go to the next level, right? Which is somewhat, so this is maybe parsec scale or light year scale if you want. This is maybe 100 light year scale, something like this. Then you can do what's called interstellar medium models. So you're modeling patches of the interstellar medium where you dump in all this energy and you try to understand, how multiple supernovae going off within a certain region of the galaxy, maybe even a black holes, all sort of work together. Then on top, again, you try to develop an effective theory for that onto sort of the 1,000 or even 10 to the 4 light year type scales. And those kind of scales, then you can run in sort of in cosmological type scenarios, right? So now you can account for all the inflows and outflows onto not only within the halos, but also perhaps extending out from the halos. And then you can, go to the really large volumes in order to sort of understand the statistics of this type of process. But in each case, what you're trying to do is trying to, parameterize it in some way. So for instance, for supernova feedback, and by the time you get to cosmological scales, it basically amounts to 2 parameters. So one is the wind speed that supernovae drive material out at, and the other is a thing called a mass loading factor, which is basically the outflow. So it's m dot out divided by m dot star. So how much mass? What is the mass loss rate in the outflows divided by the mass going into stars, the star formation rate? So by the time you get to this sort of cosmological scale, all of star formation and supernovae have been reduced to these two parameters. And you're hoping that basically, the small scale model can be modeled reasonably effectively with such parameterizations. But, other people do it other ways, of course, but that's just one way to do it, for instance.
Right. And in terms of geometry, what geometry do you use when you say 3D hydrodynamics?
Yeah. So again, it depends on the particular simulation you're doing, but typically we don't assume any geometry, right? We basically start with a volume of the universe, that is some, if it's a big simulation, maybe it actually represents a representative volume of the universe. But if you want to do things a little bit high resolution, focus on a particular galaxy, you sort of, we don't assume any geometry, but we basically, one of the, no, let me sort of, one of the most effective ways I think to study the CGM and to study individual halos is to use what's called zoom simulations, where you basically take a large volume simulation, and this is, you're talking, gigalight years maybe in size, and you pick out a small region of it, and you represent all this stuff on the outside of that region with very coarse particles, and then you represent the inside of this with very fine particles, right? And by having the outside, you're sort of getting the overall, large scale structure geometry, the torques associated with that, the inflows and outflows associated with that, but you're concentrating your computing power on this small region where you can then try to study all these more complicated processes like star formation, surface instabilities, add magnetic fields, so on and so forth. So yeah, it's kind of a, you try to sort of build up this thing, but there's no implicit geometry assumed in any of this. We're just trying to effectively model, a random region of the universe or a random particular halo that we've selected to model. So it does have to be fully 3D. We can't really, make any sort of cylindrical assumption or anything.
Okay, thank you.
Great, thank you, Romeel. Other questions? Romeel, I had a question, which is often in astrophysics, there's at least one object that behaves as expected, as we say, and that's of course the one that ends up in the textbook, and it's the rare beast. But are there some of these, are there isolated galaxies there, or things that just are easy to understand that kind of make sense, where you don't, feedback's null, or? Maybe an interesting case, but sometimes you can learn something.
I'm trying to think, but I'm actually gonna go with no. There really isn't. So, you can, people used to think that the massive galaxies, by massive galaxies, I mean, the things over in this region, way over on this side, the green stuff over here, were really simple systems, because it turns out they're not forming stars anymore, and they're surrounded by a big hot halo. You can often see this, I didn't mention this, but you can often see this gas in the X-ray. So there's a place where you can actually see it in emission for these very massive systems. Unfortunately, it looks like even that's not terribly simple, because you have to worry about, keeping the gas hot with the AGN, so on and so forth. So, I mean, there is really no galaxy that I know of any size that's been measured for which we've been able to conclusively catalog the baryon content reaching 1, or reaching the cosmic baryon fraction. Certainly, Jeff's work, I think, is one of the organizers, has done terrific jobs of trying to estimate the mass in the CGM in cool gas and other components. And, it's plausibly 1, but the error bars are also extremely large. So, I think there's no galaxy where you see this very simple picture of the 1970s seems to be holding true. Essentially, such galaxies almost don't exist.
Okay, thank you.
So yeah, Mark makes the point that that clusters, you do see the omega baryon of 1. So as I sort of drew here, once you account for the hot gas, you do get up close to unity here. The problem is the existence of this hot gas is actually a rather of a mystery, and how little of it has formed into stars and how little of it seems to be cooling is actually a big mystery. And so that's, in that sense, even though we've reached unity fraction there, we still don't understand what's going on.
Great. Okay, well, thank you so much, Romeel, for a great talk.
Absolutely.
And thanks for the questions from our staircase participants. So
I'll stop sharing here.
take a round of applause. All right. Well, thank you very much. Thanks, everybody.
Absolutely. Yeah, it was good to see you all.
Have a great rest of your Monday, everyone. Thank you.
Okay, bye-bye.
Thanks.